Hey everybody, Math 3 Honors, Friday, April 3rd. How's everybody doing? Well, it's been another week. Hope you're all doing well. Miss you guys in class. Um, I'm going to start the next lesson for you. Mod 3, Topic 2, Lesson 2. Basically just continues with our y equals ab to the x formula and just kind of expands on them a little bit with growth and decay of bank accounts and population. If you take a look at the notes, okay, I'm showing you here how we've got that y equals ab to the x formula. And that formula is going to pretty much stay the same, except we're going to do a little adding to it. Okay, here you'll see there's a growth and decay factor formula. P of t equals p times 1 plus or minus, depending on if it's growth or decay. It won't be plus or minus at the same time. To the t, I explain exactly final amount, initial, date, rate, and time period. 1 plus r is your growth and 1 minus r is your decay. There's also, when you're doing a banking problem, compound interest. A equals P times 1 plus R over N. This is the tricky part right here. Right here, because it actually ends up going to two different places. Okay, we still have our final amount. We still have our initial amount. We have our 1. We have our plus. You're not going to have minus usually here, but I like to show you this because sometimes population deals with this one. It's a rarity, but it could. Of the rate divided by the number of times it's compounded. So that means if it's compounded once a year, that n would be 1. If it's compounded twice a year, n would be 2. If it's compounded monthly, think of how many months are in a year. There's 12, so then n would be 12. Daily would be 365. Quarterly would be 4, because there's 4 quarters in a year. Okay, and then you take that n and bring it up to a power again and multiply it to the time period t. Calculator does this all for you. We're also going to get into continuous growth, continuous population, or continuous bank accounts. We haven't really talked about a natural log yet, but the inverse of an exponent is a logarithm. And one of the numbers, you know how we use pi? Pi is 3.14, which is the circumference over the diameter of a circle. In this case, this PERT formula, or NERT formula, this PE to the RT, E is just the number 2.7182818281828, and so on and so forth. So it's a little easier of a formula. There's a key E in the calculator that I'll show you how to get to in a minute. Okay, so just hang on with that. What I want you guys to do is, there are 6 graphs here that you're given, and there's 6 equations. Take your Desmos, take your calculator, take your phone, whatever you're using, put these in the calculator and see which ones match to which. Now, pay attention. There's some points given here, some points given here, some points given here. Pay attention to those points. They are huge when you're doing these. So, of course, you're going to go to your table, second graph, when you go and look for those points. So that'll be something you're going to do. Now, also, just as a quick review, we've got our exponential growth graph. Okay, that's 0, 1. And I'll draw a quick exponential decay graph. Oops, a little more slanty, sorry. That's still 0, 1. I put a line, I should have put a point there. Now they look the same. And we're going to talk about some of the things. So let's look at growth. This is where our b is greater than 1. Okay? In terms of our domain, you should be able to look at it and see from left to right, we're going from negative infinity to infinity. Bottom up, remember, this is not being touched. That's your x-axis. That's an asymptote, which I just gave you an answer. So where does that begin? It won't touch it, but it begins at 0 and goes to infinity. The asymptote is obviously the x-axis, which is y equals 0. There are no x-intercepts, but there is a y-intercept at 0, 1. So x, there's none. Y is 0, 1. End behavior, which you guys are having a horrible time with still. Remember, this function, read it as it's going this way first. Okay, where did that go? Well, it went from, as x approaches infinity, f of x approaches infinity. Okay, and then as you go the other direction, okay, so we go this way now. Sorry, I'm overlapping. Now you'll look, it's going toward negative infinity. So as x goes toward negative infinity, what's the y doing? Well, it's getting closer and closer to what? 0. You guys are making end behavior too hard. Okay, quit making it so difficult. Remember, a branch goes in 2 directions. Upward, downward, whatever. Draw a whole bunch of arrows and follow to see where it goes. And then in that first graph, that's an interval of increase simply from negative infinity to infinity. I cannot make infinities today. Okay, so that's your growth. Decay is where it's a fraction. Works the same way though. The domain is still going to be negative infinity to infinity. The range is still going to go from the asymptote to infinity. Okay, so that's no change. The asymptote is still y equals 0. Here's where it gets a little different. Oh, I'm sorry, the intercepts, I jumped ahead. We have none for my x, and my y is still 0, 1. Now the end behavior, it flip-flops. Okay, it totally flip-flops. As you can see, as we go this way, that's x approaching infinity. What's happening to the y, whoops, it's getting closer to 0. Notice that was the end behavior of the other side of the branch for the first one we did. Okay, then you flip this and flip this around. Look at it, reading it that way, and you'll see that you're going from, as x approaching negative infinity, f of x is going up to infinity. But this graph is obviously a decreasing function, so we're decreasing across negative infinity to infinity. Okay?